Welcome, everyone. Okay, let's just dive right into this explainer on section 6.3 of your textbook. Today, we are focusing on architectural patterns, which are absolutely crucial blueprints in software engineering. Seriously, if you want to understand how massive, complex software systems are structured so they don't just collapse under their own weight, you're exactly in the right place. So, let's get started. Here's our roadmap for today. We'll start with an introduction to patterns, then explore the model view controller pattern, layered and repository architectures, client-server architecture, pipe and filter architecture, and wrap it all up with a summary and exam focus.
All right, Section 1, Introduction to Patterns.
Before we look at any specific examples, we really need to define our core term. Think about it. When an architect designs a new building, they rarely invent a completely new way to build a house from scratch, right? Software architecture is exactly the same. An architectural pattern, which is sometimes called an architectural style, is essentially a stylized, abstract description of good practice and system organization that has been highly successful in previous systems. Think of them as tested blueprints. We reuse these because they represent accumulated wisdom. But remember, every pattern has specific strengths, weaknesses, and a context where it absolutely shines.
Moving right along, Section 2, the Model View Controller, or MVC pattern. Let's dive right into this first specific blueprint.
The MVC pattern effectively splits a system into three logical chunks. First, the model component, which manages the system data and any associated operations on that data. Then you have the view component, which defines and manages exactly how that data is presented to the user. And finally, the controller component, which manages user interaction, like key presses or mouse clicks, and passes those interactions along to the view and the model. By keeping these three elements strictly separate, we stop our code from turning into a tangled mess.
If we trace the conceptual organization here, just follow the flow of communication. When a user interacts with the system, those user events go straight to the controller. The controller maps those actions to updates in the model. Now, the model encapsulates the application state, so when it changes, it sends a change notification over to the view. The view then turns around, requests the updated data from the model, and renders it for the user. It's this continuous, clean loop.
Seeing MVC apply to a real-world web application really makes this concrete. Notice how the browser sends an HTTP request straight to the controller. The controller handles all the application-specific logic and updates the database, which is our model here. The model then notifies the view, which dynamically generates a brand new HTML page to send all the way back to the browser. I mean, this pattern is literally the backbone of almost every major web framework used today.
So the crucial point is understanding exactly why we use MVC, and just as importantly, when we shouldn't. The massive advantage is that it allows your data to change entirely independently of its representation. You can switch your view from a pie chart to a bar graph without ever touching a single line of the underlying model code. However, here's a trap a lot of junior developers fall into. MVC is not a magic bullet. The main disadvantage is that it adds totally unnecessary code complexity if your data model and interactions are actually very simple. Basically, don't over-engineer a simple system.
Okay, Section 3, Layered and Repository Architectures. Let's examine two styles that deal heavily with how systems organize and share data.
First up is the layered architecture. What it is, simply put, is a pattern that organizes the system into horizontal layers. But here is the golden rule. Each layer only relies on the facilities and services offered by the layer immediately beneath it. Why is this so good? Well, it's excellent for security and portability. Because of this strict separation, you can completely replace an entire layer, like, say, swapping out your bottom layer database without breaking any of the layers above it, provided the interface remains the same.
Let's look at a very concrete example from your textbook, the iLearn digital learning system. Notice the four distinct layers here. Right at the top, you've got the browser-based user interface. Beneath that, configuration services. Then, application services, like messaging. And finally, right at the bottom, utility services, like your storage. For your exam, you absolutely must understand this concept thoroughly and know how to draw a basic version of this four-layered structure.
Now, the layered pattern is fantastic for separating concerns, but I want you to ask yourself this. What if you have a system where all the components are constantly generating and needing to share massive volumes of data efficiently? Passing all that data up and down strict layers? That would be an absolute nightmare.
And that specific problem brings us to the repository architecture. In this pattern, all the data in a system is managed in a single central repository that's accessible to all system components.
The key thing to grasp here is that components do not interact directly with each other. They only communicate through that central repository. A perfect example of this is an IDE, an integrated development environment. Your Java editor, your UML editor, and your code generator, they aren't talking to each other. They're all just pulling from and pushing to the exact same central project file.
Let's weigh the pros and cons here. The main advantage is that all your data can be managed consistently in one place, which makes things like backups incredibly easy. Plus, the components remain independent of one another. However, and please pay close attention to this, as it is a major exam focus, the repository is a single point of failure. If that central repository crashes, the entire system goes down immediately. It's a huge risk.
Right. Section 4. Client-server architecture. Having just covered how components share a single database, let's transition to how distributed systems offer and consume services across a network. What exactly is a client-server architecture? Well, it's a model where the system is presented as a set of services. It has three main components. First, you have separate servers, which are really just software programs that provide specific services. Second, you have clients, which are instances of programs that call on the services offered by those servers. And third, you have a network, usually the internet, that allows the clients to actually access these distributed services.
Let's apply this to a distributed film library. Notice how the workload is beautifully split across the network. We have multiple clients accessing the system over the internet. And on the server side, we don't just have one machine trying to do everything. We have a distinct video server for the film store, a picture server for photos, and a web server for catalogs. The massive advantage here is scalability. It's incredibly easy to just add a new server to this network without disrupting any of the existing clients.
Section 5. Pipe and filter architecture. We're making great time. This final architectural style is fundamentally different from the others because it focuses heavily on data processing rather than direct user interaction.
The pipe and filter architecture models the runtime organization of a system where data flows sequentially. First, you have an input data stream. This data then flows through discrete processing steps. We actually call these processing steps filters because they transform or filter the data. The data flows from one filter to the very next via connections, which we call pipes. Finally, all that transformed data reaches the end of the line for output generation.
Let's look at a classic textbook example, a batch processing system for weekly invoices. Tracing the flow from the start, we read issued invoices. That data flows through a pipe right into a filter that identifies payments. Then the data actually splits. One pipe takes the paid invoices to a filter that issues receipts. Another pipe takes the unpaid invoices to a filter that figures out what is due, which then flows to a final filter that issues payment reminders. Each step is a distinct, isolated transformation.
Now, while this is fantastic for batch processing, like those weekly invoices, this pattern has a severe limitation. As the textbook states, interactive systems are very difficult to write using the pipe and filter model. Because graphical user interfaces rely on unpredictable events like random mouse clicks or menu selections occurring at any given time, it is just terrible for highly interactive applications. You simply cannot force a user's random, unpredictable clicks into a rigid, sequential data stream.
Finally, Section 6, Summary and Exam Focus. We've covered a lot of ground today. Let's pull all 5 of these patterns together to make sure you are 100% ready for your assessments.
So, here's the absolute crucial point for your exam preparation. You must be able to confidently list the 5 patterns we discussed today: MVC, layered, repository, client-server, and pipe and filter. Second, be prepared to draw and label a basic diagram of a layered architecture, making sure you show how services only communicate downwards. And finally, you must be able to explain the main disadvantage of a repository architecture, which is, of course, that major risk of a single point of failure taking down the whole system.
To wrap up, I want to leave you with an important reality check. While we study these blueprints in isolation to understand how they work, real-world systems are rarely just one single pattern. They combine them. For instance, you might use the MVC pattern strictly inside the top presentation layer of a massive layered architecture. Understanding how these patterns can actually interlock sets up our next lecture perfectly, where we'll be diving into larger application architectures. Until then, I want you to think about the apps on your phone. Which architectural pattern do you think is hiding behind your favorite screen? Keep learning, and I'll catch you in the next explainer.